So what I'm going to do today is I'm going to focus on one part of the lesson. Okay, let's focus on one part, the first part of the lesson, finish it off during today's discussion. And on Wednesday, we will focus on magnetic field. So I'll first introduce you to both the things, and then we will mainly focus on this part today. Okay. So my first question is, what creates a magnetic field? We have to know that before we go to magnetic force, right? Yeah. What creates a magnetic field? Or in other words, around what can you see magnetic field lines? So I got one correct answer, magnets. So we know around magnets there are magnetic fields, right? North, south. We know around when we have a magnet, field lines go from north to south. This is in the chapter 20.1 section is on magnets, right? Okay, so one is magnets and then I got another answer, current. Very good. So the other one is current. Can I have one more? Something related to current. So I will explain everything. Something related to current. What is current made up? So very good. So flow of charges. Oh, not really. We don't really need a flow. Even if we have a moving charge, then there will be a magnetic field. So magnetic field can be created by magnets. So that is what we knew from small days, right? So this is new. A magnetic field can be created by moving charges. This is very important. Moving charges should move. Moving charges, or in other words, currents. So they are kind of similar, right? So current is a flow of charges, and moving charges means even one charge which is moving is enough to produce a magnetic field. So let's now compare this part with the electric field. Can you remember how electric fields were created? What created electric fields? What created electric fields? Charge. Very good. So charge. So if we have a charge, we know around it there will be a electric field, right? So to create an electric field, we just need a charge to be there. We don't care whether it moves or not. Usually, in the previous lesson, we were mainly talking about stationary charges. Stationary means charges which are not moving. Even if it was moving, still there will be electric field. So for electric field, the condition is you just need a charge. We don't care what is happening to the charge. As long as you have a charge around it, there will be an electric field. But for a magnetic field to be created, we don't need a stationary charge. We need a moving charge. Okay, if there's a moving charge or a current, let's say this is some charge moving with some velocity, and this is a current carrying wire. So both of this will create a magnetic field around it. So are you okay with these two? How it changes with the electric field? Yes. Okay, so this is one part of the lesson. And to find the direction, so magnetic field is given by this letter. So in E field, we use electric field, we use E, right? For a magnetic field, we use B field. We call a magnetic field a B field. So to find the direction, we use right hand rule. Right hand rule. We are going to use a right hand rule to find the direction of the B field. But we are not going to focus on this part today. That is for Wednesday. Okay. So this part we will do in detail on Wednesday. Okay. Now let's think of a magnetic field. Let's say we have a magnetic field going this way. So my question is, magnetic forces, let's say I keep something inside this magnetic field. What should it be for a force to act on it? If I compare with the electric field, we know in an electric field, if we keep a charge, there is a force acting on it, right? Q times E. So in the same way, what I'm asking here is, what do you need to keep inside a magnetic field for a force to act on this object? I got one answer. Yes, so I'm getting a part of the answers. Can I have some more answers? Something moving, yes, that is correct. You need. What if you, okay, so one answer is a moving charge. So if you keep a stationary charge here, nothing will happen. This is not going to feel anything. You need a moving charge. If your charge is moving, then your charge will feel a force. Okay, medium. So if your charge is moving, then it's going to feel some force. So what else? Is it only a moving charge that will feel the force? Are there any other things? But if you keep a magnet in this, will it feel some force? Yes, right? We know, you know that like when you keep north together, they are going to repel each other. Those are forces, right? So magnets will also feel the force. So everything here is valid to this part as well. So magnetic forces can act on magnets. We know that. And also magnetic forces can act on moving charges or current carrying objects. For example, on this charge, we know a force will act. And also let's say I keep a current carrying conductor like this. So I have a wire inside this magnetic field. Then this wire is also going to feel a force. Okay. So this wire will move in some direction. So we are mainly going to focus on this part today. So let's look at this part. Let's try to calculate magnetic force acting on currents and moving charges and how to determine the directions. So are you okay with the overview of the lesson? So this is what's there in the lesson. All the equations are related to either finding the magnetic field or finding the force. Okay, so as the first step, let's start with the easy one. Easy one is the magnetic force acting on a current carrying conductor. So current carrying conductor, we know magnetic force act on currents, right? So here I have a diagram and the red arrows represent the B field. You know what B is, right? B is magnetic field. and I have this wire of length L, and it takes current this way. And this angle theta is the angle between what? It is the theta is the angle between B and I. So let's see the equation now. So this is the equation that we use to find the force. But it might look confusing at first, but it is not that confusing. So here, so first I will explain what each term is. Then we will simplify the equation. So I. So what is I? I is the current through the conductor. So current through your wire. What is L? It is the length of the wire or the conductor. Let's say conductor. We know current can be only transported through conductors. So you can just use wire also if this is confusing. So length of the wire or the conductor. But can you see that they have put an arrow on top of it? So it's like the length has a direction, right? So we usually put the arrows to symbolize vectors, right? So length vector is actually representing the direction of current. Okay? Because current is not a vector, right? We know current, although current is not a vector. Therefore, what they have done is they are taking the direction of current as the direction of length and considering it as a vector. So you don't really need it, but if you are curious about it, that is what it is. Okay, then we have this symbol. So this is not multiplication. It is something like a multiplication, which is called the cross product. And this is my B field or the magnetic field. Okay, so do you all know about cross products? Yes. Do you know about dot product? Yes. So let me think of an equation. Okay. Can you remember we learned the equation like this? Work is equal to force times distance. So we, instead of the dot product, we put a cosine theta. Remember? So in the same way, we can simplify this equation. Instead of the cross product, we can put a sine theta. So this is the equation that you will be actually using. So force is given by current, length, value of the B field times sine theta. Okay. So this equation will only give you the magnitude. Okay, it will not give you the direction because we are not, although your force is a vector, we will not be using this equation to find the direction. We'll use this just to find the magnitude. So are you okay with this equation? It's nothing hard, right? I times L times B sine theta. And theta is the angle between current and the B field. Okay. So now I'm going to draw a diagram and you all are going to tell me what your L is. Okay, let's assume that this is a B field, okay? So this is a B field and it is only in the area that I have drawn the lines. So it is only from here to here. And also I have this current carrying conductor from here to here. Let's say this whole length is L1 and the length inside the magnetic field is L2. So if I ask you to find the force acting on this wire, what you will be doing is you will be substituting values to this equation. So my problem is, what is the L that you will substitute? Is it L1 or L2? I got one answer. Any more answers? I got two answers. Okay, so your answer is correct, L2. Okay, why? So this L is the length of the conductor wire inside the B field. So this force is created by the B field, right? So if your wire is not in the B field, we don't care about these parts. We only care about the part inside the B field. So you're on here, you have to substitute L2. Okay? Is it clear? Yeah? Okay. So the next thing is finding the direction. Like I said before, previous equation, this equation. So we are not using this equation as it is, we are using this one. So this one only gives you the magnitude of force. But we have to know to find the direction because force is a vector. Okay. So how to find it? So for this, we will be using right hand rule. So there are two kinds of right hand rule. And this is the one which is hard. So this is the hard one. Not really hard, but let's say this is relatively hard compared to the other one. Okay. Other one we are going to learn on Wednesday. So let's first consider this diagram. Okay. So I'll first explain this diagram. So here I have a current carrying conductor inside a B field, and B field is this way. So what is this direction? So what is this direction? Is it into the plane or out of the plane? Out of the plane, right? So it is like this one is out of the plane. This one is into the plane. Okay. So think that we had this B field and we brought this current carrying conductor to the B field and kept it here. So it is a current carrying conductor in a B field, in a magnetic field. So magnetic field was already there. And I'm just keeping a wire which carries current. So we know there will be a force acting on it. Now let's try to find the direction. Okay. So your first step is take your right hand. So if you use left hand, your answers will be completely wrong. So make sure you are using your right hand because it is a right hand rule. Next step, you can see me, right? Next step is point your fingers, this stuff, not the thumb, everything else. So I have written down the steps. You have to point your fingers along the current. So my current is this way. So this is my left hand. So you might see that I'm kind of flipped. Okay, so you can keep your hand just like in this picture, in the slide. So current is going this way towards my left hand side. So keep your fingers towards left. Yeah. And after that, you need to curl your fingers, the set of fingers, towards the magnetic field. So magnetic field is out of the plane, right? So towards your face. Magnetic field is towards your face, right? Out of the plane. So I'm going to curl my fingers towards my face. The direction that my thumb points is the direction of the force. So are you okay with that? So you keep your fingers like this. So you keep your fingers pointing along the current, and then you curl your fingers towards the direction of your B field. And an important thing, when you curl your fingers, let me look at myself whether I can see myself. Okay. So when you curl your fingers, you have to make sure you always curl into your palm. See? Into the palm. So like this, just like a thumbs up. So don't do this, okay? I've seen people try to do this. So you can't curl your fingers other side, you will break your hand. So like this. So now I want you to repeat the same thing if the current was going the other way. So the answer is downwards. Okay, so we have more than enough examples here. So tell me one by one. So let's see what we are getting. So I'm going to look at myself again. Okay, so this is my hand, right hand. This is my left hand side. So I have my left hand here. Okay, so my first step is current is going that way, right? So current is going that way with an angle. But I can't keep my hand just like this because I need to bend my fingers upwards. B field is upwards. So for that I need to keep my hand like this, right? Palm facing up. My palm is facing toward the ceiling. And my hand is with an angle because the current is with an angle. Okay. And now I'm going to bend my thumbs towards up. Can you see my thumb is that way, pointing out of the page? Yes. So my thumb is pointing out of the plane, out of the plane. So did you get it? Yes. So if I, this is a trick that I usually do, trick time. So always have your palm, okay, always have your palm towards the direction of the B field. Then it is easy to figure out the direction. So my B field is upwards, right? So I start like this. Then I point my fingers like this. It's an angle. Then I can curl it easily, right? So this is a trick. Start with your palm facing the direction of B. So start like that and do everything else the same, okay? fingers pointing along I and curling the fingers towards B. So do it and tell me the answer. So I'm getting the answer for the second one out of page. So for this one also out of page. So let's see if my trick works. So my B field is upward, so I'm just going to start like this. Current is facing that way. You can see me, right? Let me look at myself. This way. And I'm bending my fingers like this. My thumb is pointing out of the plane. So this is correct. And the third one. That is, okay, let's me start like this. This is that. So can you do it? No, right? You can't even bend. See, my fingers are pointing upwards. And I have to bend my fingers upwards. So no one can do that, right? So this is not possible. So no direction, right? So let's see what's the problem with this when we calculate it. Okay. So this one we couldn't even bend our fingers. So now let's go to the last one. What is the answer for the last one? So after we figure out the directions, we'll figure out the values. Yay. So you'll are getting the answer. Right. Yeah. So did it become easy with my trick? So my thumb is pointing. So B field is upward, so I just keep my hand like this. But my current is into the plane, right? So I just kept my hand like this. Thumb is towards the right side. Right. Easy, right? So practice this as many times you can. Okay. Okay. Now let's try to figure out the values. And also let's try to figure out what is happening in this one. We couldn't even turn our fingers. Okay. So for the first one, we know force is given by current times the length, what else? Times B times sine theta. So can you tell me what is theta here? Is it 30 or something else? What is theta? Theta is the angle between B and I, right? So what is your theta? No answers? Finally I'm getting answer 60. Yes, it is 60. Why? Because we need the angle between B and I. So this is my B field. B field is this way, current is this way. So this is my angle, right? They have given this angle, which is 30. If this is 30, this is 60. Okay. So what is, so this one. What is the sine value in this? 90. Sine 90 is 1, right? Sine 90 is 1. So you get ILB. So do you know how the sine curve varies? So a sine curve varies like this. Okay. So the maximum value sine can take is either positive 1 if we just take the magnitude or a negative 1. So the sine always varies between plus and negative 1. Plus 1 and negative 1. Okay. So at 90, this 90, it is 1. Let's see what is happening in this one. So what is the angle between B and I in the third one? What is your theta? What is theta? They are along the same direction, right? So they are along the same direction means 1. If they were like this, then 180. Okay. If they were opposite, then 180. If they are in the same direction, it is 1. Sorry, it is 0. So there is 0 and 180. So it is like this, right? So your sine, your theta is 0 and sine 0 is, what is this value? Sine 0. 0. So when you have it like this, your force is ILB times 0, right? This multiplication. So your force is 0. That is why we couldn't even bend our fingers. How can it give a direction when there is no force, right? Okay. So this one. What is the angle? What is the angle between I and B? 90. So it is also 90. Why is it 90? So here I have two pens. So one is current, it is pointing into the screen, and other one is up. So if I turn it like this, you can see it is 90. Okay. This also gives you ILB. So can you see that whenever your current and the magnetic field are perpendicular to each other, you get the maximum value. So the maximum value it can have is when they are perpendicular. Yes. And the minimum is 0. That is when they are parallel. So B and D were perpendicular. These were perpendicular. That is why we got the highest possible value. And when they are parallel, we got 0. And this example is a value in between 0 and ILB. So sine 60 is a value. It's half, right? Let's see. What is the value of sine 6? Is it sine 60? Yeah, it is. No, that is cos 60. Okay. Sine 60 is a small value less than 1. Okay, let me get the value. Sine 60 is 0.86. So 0.886 ILB. So this is smaller than ILB, right? So this is the maximum you can get. Sorry, this one and this one. So are you okay with finding the directions? Yes. Okay, so let's move to problems. So here are 3 problems. Do them and tell me the answers. So your answers, most of your answers are correct. A, B, C. I think A, B, C. A, B, C. So I'll start the first one. A 2-meter wire carrying a current of 0.6 amps is oriented parallel to a uniform magnetic field. So if your current is like this, your magnetic field is also like this, right? So that's what they are saying. It is parallel. So we know the equation has a sine term. So it is ILB sine 0. Why? Because they are parallel, right? Theta is 0. So it makes the value 0. So no force. So if you remember at the beginning, I said when we need like to have a magnetic force, we need a current carrying object or a moving charge in the magnetic field. But that's not enough, right? The current should be not parallel to have a force. Even if you have a current in the field, it's not enough. You don't need a parallel current to the field. If you have a parallel current, there's no use, no force. Okay, so the second one. So they are asking, what is the force per meter? What is that? They're asking force per length, right? Okay, let's say we don't know what that is. Let's do the problem in a normal way and let's figure out that part at the end. So they have given us the current and the magnetic field and also the angle, right? So if I use the equation, this is the equation. So let me plug the values. This is what we need to find. What is I? I is 5 and they haven't given us L and they have given us B. They have given us B and sine 27. So the next problem is what to do with two unknowns. Then we read the question again. They are asking us to find force per meter, right? In other words, what they're asking is F over L. So let's bring this L to this side and then we can do the problem. So when you do this, you should get the answer B. And the units are newtons per meters. Why? Force is in newtons and length is in meters, right? Newtons per meter. Okay, now let's move to the third one. So it might look hard in the beginning. They're asking something about minimum current. So when you just look at the question and just read minimum current, it looks hard. So what I'm going to do is I'm just going to do the problem using what I know, using the equation. And at the end, I'm going to figure out what the minimum current is. Just like what I did here. I wasn't sure what they're asking for, force per meter. So what I did was I did the problem and here I could see it, right? We can see, oh, they're asking for F over L. So I'm going to do the same thing for this problem. A thin copper rod, 1 meter long, has a mass of 0.5 kilograms and it is in a magnetic field. Find the minimum current in the rod. What is the minimum current in the rod needed in order for the magnetic force to cancel the weight? Okay, so let's say this is my current carrying conductor and it has a weight, right? And your magnetic force should be opposite to your mg for them to cancel off, right? And also they should be equal. So what I'm going to do is I'm going to equate the magnetic force and mg. Why? Because that is what they're asking in the problem. What is the magnetic so the saying magnetic force cancels the weight. So that is what I did. To cancel, they should be equal. Okay. So I'm going to rearrange them. I'm going to write mg in this side and fb in this side. So what is fb? Fb is given by I L B sine theta. They're asking for the current. So if I make current the subject I get mg divided by lb sine theta. Okay, now we have a problem. Why? We don't know the value of theta, right? Now we read the question again. Oh, they are asking something about minimum. Maybe the value of theta has to do something with it, right? Okay, so I'll write the equation here again. I'll write what we got there here. We know mg and lb are constants, right? They are values. And we definitely know the values of those. We can't change those. But we can decide the theta so that our current is minimum. So we know that we need to get the minimum value. To get the smallest value possible for current, our denominator should be the largest, right? Biggest value possible. For example, let's say you are dividing 5 by 10 and 5 by 1. So when you divide by a larger value, you get a small value, right? When you divide by a small value, you don't get a small value. Yeah. So we need to divide by the largest possible value for sine theta. So what is the largest possible value for sine theta? Sine theta can't go beyond 1, right? The maximum value sine theta can have is 1. In other words, yes, sine 90. So I is minimum when sine theta is maximum. In other words, when this is equal to 1 or theta is equal to 90. So that leaves you this answer, mg over lb. Sine theta is 1, so it is 1. So what is the answer you get when you substitute the values? M is 0.05, G is 9.8, L is 1, and this is 0.1. So when you do that, you should get the answer C. Okay. So are we okay with this? Yeah. We have another question. So I want you to do this quickly. To do part A, I want you to first find force on this part of the loop. Okay, this part 1. Then find me the force on this part. And at last find me the force on this part. I mean the direction of force. Okay, so use right hand rule and tell me the direction of 1, 2, and 3. And once you do that, the problem is easy. Okay. I am getting correct answers, a lot of correct answers. Left, right, down. Correct. So let me also do it. For this one you all are saying left, right? This one you all are saying right. And for this one you all are saying down. So let me do it. So let me use my trick. Let's see whether it works. So I'm keeping my palm towards me out of the plane. And current is going downwards for the first one. And I'm curling my fingers towards myself. This is my left hand. So my thumb is pointing towards left. So this is left, it is correct. And again, current is this way. Palm is facing towards me. It's not a rule, but it's just my trick. like this, and B field is this way. So towards right, it is also correct. The last one, current is, how do I do current? This way. Current is this way. B field is like this, down. So all are correct. And what can you tell about the forces acting on 1 and 2? They cancel off, right? Because we can see from the diagram they have the same current, because it is one loop, right? The same current flows through the whole loop. They have same lengths. This part and this part, they look symmetrical. So L is the same. We know B is anyway the same. It's in the same magnetic field. And theta is 90 degrees for both. And they are opposite to each other. So they cancel off. So forces on 1 and 2 cancel off. This and this get cancelled. And you are only left with this, right? So your answer for part A is, find the direction. It is down, right? Downwards. And for part B, they have given the values and they're asking you to calculate the force. So we know only force acting is this one. And theta is 90. So can you plug the values and give me the answer? So correct answer 3. I is what? 5. Magnetic field is 3. What is the length? Length is 20 centimeters. 20 centimeters is this times 3. Did I do something wrong? I think yes. No, right? 3 newtons. So this point 2 came from 20 times 10 to the negative 2. I converted it to meters. Okay. So shall I move to the next one? Yes. Okay. So here we have the next part, which is the force acting on charges. What charges? Moving charges. So it is exactly same as current, but the equation is little different. So the force is given by this equation. So for a current, so the equation for current was this, right? I L cross B. We know for a charge we have a for a moving charge we have a value for charge Q, and it needs to have a velocity to move, right? So the parameters for a charge are Q and V, just like length and I for a conductor. Okay. So can you tell me the equation that we can use instead of the cross product for this one? What should it be? So if we get rid of this cross product, what's the equation? No equations. Okay, QVB sine theta. And theta is the angle between V and B. Okay. So I think you all are okay with this. And the way you apply the right hand rule is exactly the same. The only difference is instead of the direction of current, now you have the velocity, right? It is the direction of charge movement. Now this is important. Unlike current, we can have positive charges and negative charges, right? So current is actually a positive thing, right? Current is the movement of positive charges. So when you apply right hand rule for a positive charge, direction of your thumb gives you the correct direction of force. So what you do is, if you have a moving charge, let's say you have a moving charge, you apply the right hand rule in the normal way. Then you look at the charge, the sign of the charge. If it was positive, you use the same direction you get from the right hand rule. If your charge was a negative charge, you flip it. You take the opposite direction. If the right hand rule gave you direction up, for a positive charge, it is up. But for a negative charge, it will be down. If the right hand rule gave you left, for a positive charge, it is still left, and for a negative, it will be right. If the right hand rule gave you out of the plane, into the plane, for a negative charge, it will be out of the plane. So you use right hand rule to find the direction. If it's positive, keep the direction as it is. If it is negative, flip it. Okay, so here are 3 examples. Apply a right hand rule and tell me what do you get for a positive and what do you get for a negative. Okay. What are the directions you get for positive and negative? Okay, for A, I got the answers from you. So I got left and right. Is it correct? So for the first one, your hand is like this, yeah. So left, and if the charge is negative, right. For the second one, this way into the plane. So this is in, this is out. So for the third one, my hand is into the plane, my palm, but my current is going, my charge is going that way, up. So for a positive one, it is up. If it is positive, if it's up for this is down. Okay, this is exactly same as what we did for currents. Only thing is, if your charge is negative, you flip it. Okay. Now, do this problem and tell me the answer. It is just a substitution. Yes, it is B. So if I use the equation QVB sine perpendicular means sine 90. Q is 1.6, 10 to the negative 19. V is 5, 10 to the 4. B is 0.2 and it gives you the answer B. An important thing that we have to know is when we use this equation, always remember this gives you the magnitude. Okay, so don't plug negative or positive values because this only gives you the magnitude. Okay, so just give the magnitude as the answer. And if they give us enough information in the problem, we can find the direction using right hand rule. Okay. So this is the next part. So moving charges are interesting than currents. So what happens is, let's say we have a charge moving this way. So forget about the B field for now. Let's assume that we had a charge, positive charge or negative charge, moving this way. And suddenly I turn on the magnetic field. Okay. So suddenly I turned on the magnetic field. So now my moving charge is completely inside the magnetic field. Okay. So if you use your right hand rule on this charge, you will see that the force is upwards. So what happens is, since the force is upwards and this is moving this way, it will go along a path like this. So that will happen continuously. Okay. So eventually you will see that the charge starts to move in a circular path. Okay. So when there is a moving charge, completely, so this is very important, completely inside the magnetic field. Okay. Completely inside the magnetic field, very important, completely inside the magnetic field, and the velocity and the magnetic field are perpendicular. See, they are perpendicular, right? Out of into the plane and this way. What happens is your charge will start circling. So that is one instance. The next instance is, unlike the previous one where your charge is completely inside the magnetic field, now you have a charge, let's say you have this charge entering the magnetic field. Okay, it just entered. So when it entered, the force acting on it will be this way and it will go around a circular path. But since it's not completely inside when it started, it will only go a half a circle. It will go in and come out. Okay, so they are two different things. Although they are both circular paths, they are both following circular paths. But if your charge was completely inside the magnetic field, then it will go around a full circle. If not, if it was just entering the magnetic field, it will go a half a circle or some portion of the circle. So are we okay with that? So these are like two things that you have to know. Completely inside full circle, entering it half a circle. So can you look at this diagram and tell me, to go in the circle, what gives the charge the centripetal force? So we know for anything, for any object to go in a circular path, you need a force towards the center, right? We need a force towards the center. So in these examples, force is provided by the magnetic field. F is equal to QVB. But like I said at the beginning, in these two scenarios, always your velocity and B field will be perpendicular to each other. So your sine theta is 90, right? So it leaves you QVB. So magnetic force provides the centripetal acceleration. You remember this, right? From old stuff, mv squared over r, mv squared over r. So this is the centripetal force, remember? Mass F equals, you remember F equals ma? Yes. So acceleration in circular motion, which is called the centripetal acceleration, is given by v squared over r. So that is what I just did. I equated my force provided by the magnetic field to ma, mass times v squared over r. So this is my force provided by the magnetic field QVB. So this gives me a new equation. So if I simplify this further, QVB mv squared over r. So this v get cancelled with one of these v's. And if I take this r to this side, I get this equation. So this equation, they might not have this in the formula sheet, but you should be able to quickly derive it. It's easy, right? FB, just equate it to mv squared over r. That's all you need to do. FB is QVB. Then we get cancelled and you get R. I don't think that they give this in the formula sheet because this is like an application. It's like a problem, although I teach it separately. Okay, so whenever you see charges inside magnetic field, if velocity and the B field are parallel, and if it's completely in, it goes around a full circle, and this is the radius of the circle. And if it's just entering the magnetic field, it will go half a circle, and still this is the radius of the circle, half a circle. So all this time I was talking about when V and B were perpendicular, right? What if it came with an angle? So they might not ask you problems with that, but they can ask you conceptual problems. So if you check in the textbook conceptual example, so it is in the inside the chapter, not the question side. It's an example. They say that it will not go around a full circle. What it will do is it will go around a helical path, something like this, something like a curl, some curly path. So it will go like this. It's a helical path. So they can ask these stuff in conceptual problems, okay? So if V and B were perpendicular, then circle or half a circle, depending on where your charge. Okay, if it was just entering half a circle, completely inside, full circle. If V and B were not perpendicular, it will go in a helical path. So please check this example in the textbook, okay? It's not a problem, it's like they explain how it happens. Okay, let me check the time. Okay, we have few minutes. So if I go back, I'll write this equation. R equals mv divided by qb, right? So we will need this. R equals mv divided by qb. So can you tell me the answers for the first one quickly? So it is circular path. Now that you know what is happening, you know the path. So charged particle is injected to a magnetic field. So it is something like this, right? It is just entering. Injected means they just enter it, right? It just enters the magnetic field. We know it will go around it and come out. So it is like a half a circle, but they are not digging that deep. They are just asking what is the shape of the path. It is a circular path, but really it is a half a circle. Okay, a charged particle is observed traveling in a circular path in a uniform magnetic field. Okay. If the particle had been traveling twice as fast, what would happen to the radius? So can you see that these problems are very common? You will see them in exams. So to answer this, you have to know how to get this equation. So if you have this equation, doing this problem is not hard. So there are two scenarios, right? First one is normally going in this circle. And the next scenario is, what if the speed is twice? Let me write a new equation for that, R2. M, I'll just write R for this and R new for this. Okay. M, now my V is 2V. It is twice divided by QB. So if I rearrange this, 2 times MV divided by QB. What is this? This is same as our old R, right? So if your speed is twice, then radius doubles. Okay. So these problems are not hard, but you have to kind of know the equation, how to get it. Like practice few times to derive this. So the last one, a particle carrying a charge of plus E travels in a circular path in a uniform magnetic field. If the particle is now 2E, so what they do is now they double the charge and they ask for the radius. So let me write R new, just R new for this. M, V, they twice Q, right? 2Q or 2E, anything. So they made it twice. So if I rearrange this is our old radius, right? Old stuff, MV, QB. So what has happened to the new radius? It has become half. 1/2 of the original value. Okay.